I'm Sarah Abrevaya Stein. I have the honor of being the Stadium of the Con Director of the Alan D. Leve Center for Jewish Studies. I'm also a professor of history and hold the Viterbi Family Chair in Mediterranean Jewish Studies. And it's really a pleasure to have you here in person. So wonderful to be gathering. I want to begin by welcoming you and begin really by taking a moment to honor Alan D. Leve, who alas is not joining us today, but for his generosity in envisioning an event like this and a center like this. Through his support and the support of his family represented here today, our center has been able to nurture exemplary scholarship, to support students at the undergraduate and graduate level, and to situate this center, the Alan D. Leve Center, as a global hub for the study of Jewish culture, the Jewish past, Jewish languages and literature, and the Jewish future. And we are so sorry Alan could not be here tonight. Before I proceed with the fun stuff, which are the introductions, I want to offer some thanks also to the staff of the Leve Center, Wu, Raina, Viv, Chelsea, for all their hard work in pulling this event off, and for the partnership with Lindsay and Yarel in organizing this event so elegantly as always. Thank you. As COVID numbers rise in Los Angeles, we urge you to be considerate of those around you and wear a face covering. It is not actually a requirement, but I will be wearing one and I welcome you to join me. And I finally ask you to take a quick moment to silence anything on you that makes noise by Virginia phone. So this week, the world got its first ever look at Sagittarius A, the supernova, the black hole in the center of our galaxy. To most of the world, this was a revelation, but to our guest, it was like seeing an old friend for the first time. Dr. Andrea Ghez, professor of physics and astronomy, and Lauren B. Leichman and Arthur E. Levine Chair in Astrophysics, is one of the world's leading experts in observational astrophysics and heads UCLA's Galactic Center Group. Best known for her groundbreaking work on the center of our galaxy, which has led to the best evidence to date for the existence of supermassive black holes. She has received numerous honors and awards, including the Nobel Prize in 2020, and became the fourth woman to be awarded the Nobel Prize of Physics, sharing one half of that prize with Reinhard Genzel, the other half being awarded to Roger Penrose. The Nobel Prize was awarded to Dr. Ghez and Genzel for their independent discovery of a supermassive compact object, now generally recognized to be a black hole, in Milky Way's galactic center. She's also received the Crawford Prize in Astronomy from the Royal Swedish Academy of Science, the first woman to receive such a prize, the Beccaria Medal from the Royal Society of London, the MacArthur Fellowship, election to the National Academy of Sciences, the American Academy of Arts and Sciences, and the American Philosophical Society. So we in the world of Jewish studies say she's really no schlub. When announcing Gez's and Genzel's recipient of the Nobel Prize, the New York Times wrote that the pair were being rewarded, quote, for their relentless and decades-long investigation of the dark monster here in the center of our own galaxy, gathering evidence to convict it of being a supermassive black hole. Her work on the orbits of stars at the center of the Milky Way has opened up a new approach to studying black holes, and her group is currently focused on using this approach to understand the physics of gravity near a black hole and the role that black holes play in the formation and evolution of galaxies. Advances in high-resolution technology, imaging technology, enabled Dr. Gez's work, and her group continues to work on pushing the frontiers of these technologies forward. She serves on several leadership committees for the Keck Observatory, which hosts the largest telescope in the world, and the future 30-meter telescope. Ghez is very committed to the communication of science to the general public. We are fortunate for that. And also committed to inspiring young girls into science. Her work can be found, therefore, in many public outlets, including TED, NOVA's Monsters of the Milky Way, Discoveries Swallowed by a Black Hole, and Griffith Observatory. And I noticed that to the Nobel Prize Committee, Dr. Ghez confided, and now I'm quoting from her, "I often tell my students that the most important decisions you make, especially later in life in grad school and even in college, is who your mentors are, who you work with, because they just play such an important role in your professional development. You really want to work with people who have your back, who want to encourage and nurture your development as a scientist." Now, Dr. Ghez grew up in Hyde Park, Chicago, a lover of puzzles. She earned her BS from MIT in 1987, her PhD from Caltech in 1992, has been on the faculty of UCLA since 1994. Of the scientific process, she has said, I'm quoting again, "It's really important to realize that hiccups are a natural part of doing research. And that's why I think that the ability to deal with hiccups is so important. Research and discovery is about exploring our frontier of knowledge, where we don't know, we don't have everything worked out, it's not neat and tidy. I think it's an acceptance that things are hard and messy, that things are complex. Your job as a scientist is to figure them out. You have to relish the mess." Now, in this time of our very, very messy world, these are words that find broad application beyond the realm of astrophysics. Before I announce Dr. Gez's presentation, I want to also say that we are here not only to listen to Dr. Ghez, but to award her the Alan D. Leve Prize. And somewhere in my notes here, I have a description of the prize. The vision of the prize was to honor someone who has contributed not necessarily to the Jewish community, but to all of humanity. And this is so very clearly exemplified in Dr. Gez's work. Today, we have before us 2 awards that I will not actually lift ceremoniously, but I'm very pleased to extend to Dr. Ghez in recognition of this award and of her incredible monumental scholarship. And I invite her to the podium to speak with us today on the subject, "The Monster at the Heart of Our Galaxy, from the Possibility to the Certainty of a Supermassive Black Hole."
Sarah, thank you for that very kind introduction. And it did inspire me. We were having a little chat ahead of time. She said, "You don't have to out yourself in terms of your relationship with the Jewishness." But that introduction really inspired me to share a little bit about my parents, because my parents were my first mentors and the first people who had my back and inspired me to think I could do anything. My parents shared a lot of things in common. They shared a passion for education and a passion for the arts, but they were incredibly different people. So I grew up in a messy environment, so I have an incredible comfort with mess. And just to give you a little bit of a sense of this, my dad was a European Jew who moved around a lot because he grew up in Europe at those times when things were complicated. He was from a family that was very well educated, so getting degrees was no question in his mind. And the urban experience was very much his background. He married my mom, who is from a tiny town in Massachusetts, who didn't go to college, whose father was a house painter, and a Catholic. So they came from very different perspectives, and today I'm so grateful for that, because I think it teaches you to have an acceptance of different perspectives and a ease with messiness. So that's my little backstory. Coming much further forward, I've been really pleased to be at UCLA for the last roughly 27 years. I came to UCLA 1 year out of a PhD. So UCLA hired me very young, which I think is really emblematic of the institution that's willing to take risks. So in hiring me, I think they really did embody that risk-taking frontier spirit. And from my perspective, the reason I felt like I feel today still that I have the best job in the universe is because I wanted access to the Keck telescopes. These are the largest telescopes in the world, and if you're in the field of astrophysics, the study of the universe, you need the best tools. And so the University of California really has the best tools in this. And it was a facility that was opening up just as I was getting to UCLA, so I really understood that this was the tool, this was the lab that I wanted to have access to. So I really have a lab here. It's out in Hawaii, which isn't a bad place to have to go to work, but I spent most of my time here at UCLA. Let me also share a little bit of the UCLA story in terms of understanding how to get into this game. So this is a telescope that's invested by the University of California. It's not a UCLA telescope, it's a UC telescope. And the headquarters for astronomy is up at Santa Cruz. But UCLA thought, and it's a great location for the headquarters, so I'm not, I can share with you why that's a great center. But UCLA was thinking about, well, how do we play a leadership role? And it turns out there was a new technology that was coming up just at this time. And so the university made a huge investment in this arena. So I'm part of that investment. And so again, it was sort of UCLA thinking very strategically about how to be in a leadership position at the frontier. Okay, so that's a little bit of the backstory about both UCLA, why I want to be here, and why UCLA positioned itself so well. So when I started the work, this is the picture from the very beginning. This is back in 1996, 2 years actually after the work started. And I'm pictured with my two senior colleagues who were part of that vision of seeing the path forward, Eric Beckman and Mark Morris, who I've worked with for the past 2 decades. And on the right is my very first graduate student. So we were a lean and mean team. And I was so excited. I thought I had a really good idea of how to use this telescope when I got to UCLA. What I wanted to do was ask the question, is there a supermassive black hole at the center of our galaxy? And I thought you could use the telescope in a new and different way to answer this question. So I put my first proposal in, and what came back was the word no. We don't think your technique will work, but even if it does, we don't think you'll be able to achieve this experiment. And I'd love to show this, especially to the young students in this group. I know I met a freshman in physics just before the talk, because it's a reminder about the hiccups along the road, and not, if you have a good idea, if you're convinced yourself, don't fold. Understand, actually what I'd like to say today, this is absolutely my favorite expression, every challenge is an opportunity. Sometimes you just have to look really hard. And in this instance, I had to understand that I was part of a new university system who hadn't heard about my ideas, who didn't know about these new ways of using the telescope. So it was my job to go up and down the UC system and give talks, basically to do the advocacy that we're actually not taught to do in graduate school. Today, the team looks very different. We're a team of about 24 people. So it's a big collaboration, and there are 2 people I'd like to highlight in this picture. One on the far left, who's Jessica Liu, and then just to my left is Tuan Do. They both started as graduate students in the group, and now they're professors in their own right with their own students who are part of this team. So it's a multi-generational, multi-institutional collaboration. And now we have a very different position with respect to this telescope. We've now become what's called a key science project for the development of new technology on this facility. So we're no longer trying to convince, but rather very much in a leadership role with respect to UC's really big investments. Really fun and exciting, but very different place to be 2 decades later. Okay, so let's look at what is it that we're doing. So we're trying to study black holes in the center of the galaxy. And we do this, as I'll get to, by studying orbits. But you might ask, why do you want to do this? Like, why is this interesting? The big so what question. And there are two really big perspective answers to that. One is one that I would say from a physics perspective. We just want to understand how the universe works. We want to understand, do these really exotic objects exist in the universe? And that's a key question, because these objects represent the breakdown of our understanding of physics. The way to think about, well actually I'm going to pause on that. I'll get to why this breakdown. Actually I'm not, I'm going to go for it. I'm just going to go for it. Because it really explains why I'm going to put this Einstein in, holding an atom. So black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light. So we're actually, maybe we could talk later about the image of a black hole with that definition. But that's the definition of black hole. And a black hole is an object whose pull of gravity is so intense that it's going to collapse to an infinitesimally small object. So I mean, in spite of the fact that it has lots of mass, it has no volume. Which is that's a hard concept to think about. I mean, even when I think about that, it's like, that's a very odd and non-physical thing. So if you think about density, which is just mass divided by volume, you're divided by 0, so it goes to infinity. And in physics, anytime something goes to infinity, it's called a singularity. And it's like a giant red arrow that says, you do not have your description of the physical world correct here. So in other words, there's more to learn. And this is why physicists love to study black holes, because they're basically the frontier of knowledge in terms of how these ideas of how gravity works are breaking down on very, very, very small scales. So opportunity to learn more. Okay, so that's a physics perspective on why asking this question is interesting. Then there's an astronomy and astrophysics perspective on why this is interesting to ask. In fact, when we first started reporting our results of finding a supermassive black hole at the center of our galaxy, people used to ask, what is the relationship between the two things? Which came first, the black hole or the galaxy? And this is like a chicken or the egg question, which came first? And today we understand that that's actually even the wrong framework to ask, because the mass of these really big black holes seems to correlate with the mass of the central part of the galaxy. So in order for those two things to be at all related, given the vastly different scales, they had to form together synergistically, and there has to be some feedback that keeps these two things in sync. Okay, so really today, one of the important pieces of our work is driven by the question, what role do black holes, these really massive black holes, play in the formation and evolution of galaxies? Okay, and galaxies are basically the building blocks of the universe. So those are two different perspectives, both of which we can approach with our work. Okay, so we've said black holes are objects that have no finite size, infinitesimally small objects. However, there is an abstract size that we can associate with the black hole, popularized by Star Trek, the event horizon, the point at which no light escapes, but named after Schwarzschild, who recognized the importance of this size. Abstract, it's not a boundary, it's just conceptual. Every black hole has one. It's the point at which light can escape. So it's actually an information barrier. You can't study what's inside that scale, and vice versa. But in a sense, it's this conceptual piece is important for understanding this talk. If I want to prove to you, and your job is to be skeptical, that there is a black hole, then I have to show that there's some amount of mass inside its Schwarzschild radius. And the Schwarzschild radius just depends on mass. You double the mass, you double the Schwarzschild radius. Okay, all right. If you squeeze something down to its Schwarzschild radius, it will become a black hole. So in other words, you could become a black hole, or more, something you probably prefer to turn into a black hole. Your cell phone could be turned into a black hole. You just have to get it down to that size, and then gravity will overcome all other known forces. Okay, so in astrophysics today, we think that there are two different kinds of black holes that actually exist out there in the universe. And these two kinds of black holes represent actually the beautiful interplay between theoretical studies and observational studies. So the first kind that were recognized recognized through theoretical studies. In other words, people just thinking what will happen next to the most massive stars in our galaxy. So those are stars that are roughly 30 times the mass of the sun. I like to call these stars, they're like the party animals of the stellar world. They live fast, die young, and do it sort of explode. So they explode at the end of their lives as supernovas, which is what we see here. Very energetic. Actually, in terms of the chemistry of our universe, these explosions are critical for creating all the chemical complexity that we take so much for granted. I don't care about that stuff for this talk. What I care about is at the middle of this, gravity's going to win and make a little black hole. And by little, I mean, well, it's roughly 10 times the mass of the sun. So we begin with theory, with the prediction that these things should exist, and then observations came along and demonstrated beautifully that these small black holes actually exist in our galaxy. Gravitational waves in the past 5-10 years have proved that really phenomenally well. Okay, so these are the ordinary black holes, if there could be such a thing as ordinary black hole. What I care about are the supermassive black holes, which are the ones that are 1 million to 1 billion times the mass of the sun, and has the unimaginative name of a supermassive black hole. And the game here, or the story, or the history here is very different, because it wasn't theorists that told us that they predicted that these things should exist in the universe, but rather it was observers, people who used telescopes looking at the universe that saw phenomena that suggested their existence, and then the theorists have to go to work to explain how they form. Okay, so what led us to think about supermassive black holes? This is a beautiful picture taken with Hubble Space Telescope. It's a very deep, long exposure picture. Everything in it except one star in the middle. You can see this. Wait, that's a star within our galaxy, but everything else is a galaxy. And a galaxy typically contains roughly 100 billion stars. So really different scale than that last picture. We were looking at one star. Let's focus our attention on the top left. There's a spiral galaxy. I'm going to show you a zoom in a moment of that guy. So that thing has 100 billion stars. There's nothing in this picture that suggests the existence of a supermassive black hole. We see stars, lots of them. Okay, so, and this picture is taken at wavelengths that your eye would respond to, so an optical, visible light. But it was pictures that were taken closer to where your cell phone works, out at radio wavelengths. And this is a picture of one galaxy, and the galaxy is sort of nestled in close. And what you see at radio wavelengths are these jets of emission just beaming out from the middle. And you can measure how fast these things are moving. They're moving at tremendously high speeds, which means that there has to be some central engine powering this phenomena, and it's coming out from the middle. In the middle, there's also light that doesn't look like starlight. And so it was these galaxies, which we call active galactic nuclei, simply because their nuclei or centers are active, so unimaginative. 10% of all galaxies look like this. In the, trying to humanize this, I like to call these are the prima donnas of the galaxy world. They're kind of show-offs. They emit a lot of energy. And it was that energy that said, well, maybe we should be thinking about supermassive black holes that have the gravitational energy to drive this kind of amazing phenomenon out from the center. Okay, so that was the story roughly half a century ago, is that, well, maybe these really big ones. Oh, and the energy in the middle was believed to be driven by the black hole accreting matter. In other words, matter falling in through the event horizon, heating up. Or, as astronomers like to say, it's like watching supermassive black hole's dining habits. So this would be a black hole that's having an enormous Thanksgiving feast, is emitting a lot of hot energy right outside the event horizon, which is what we're seeing shine in the middle. That gave people the idea that maybe all galaxies have supermassive black holes, but those black holes in other galaxies are black holes that are on a diet. There's just nothing accreting, nothing driving the energy. Because remember, black holes themselves don't emit light. Okay, so if you keep it free and clear, it's just going to bubble away and leave things well enough alone. Okay, so when we get into this picture, we're looking at trying to ask the question, do supermassive black holes really exist? And exist in ordinary garden variety galaxies like our own. So if we could get outside our galaxy and look back, so galaxies are flattened disk-like structures. So we're looking face on here. Our sun lives about halfway out in one of these spiral arms. So the other analogy I like to make here is we live in the suburbs. It's low density, things are calm, nothing's extreme, and we want to look at the center of the galaxy, which is like an exciting, dense, extreme urban center. Okay, so think downtown New York. I mean, Los Angeles isn't quite the right analogy, but everything is more extreme, and lots of extreme astrophysics happens at the center, and this is the region that we're looking for the black hole. Okay, now, the advantage of looking at our own center of our own galaxy, the Milky Way, is that it's the closest center of a galaxy that we'll ever have to study. The next closest galaxy is about 100 times further away. So, the advantage of looking or studying our own galaxy is that it's close. But as in life, for every pro, you usually get a con. And the con in this case is that we live in our galaxy, and not only is there a lot of stars in our galaxy, but there's a lot of dust. And we live in Los Angeles. We have hopefully a very good appreciation for what dust in the air does. It's like smog. It obscures your light of the local mountains extremely well. And that's because the dust particles are about the size of the wavelength of light that your eye detects. So you can't see the center of the galaxy. And this picture hopefully captures that. This is a photo from the side of Mauna Kea, which is where the telescopes are. You see the plane of the Milky Way. In fact, you can probably see why our galaxy was called the Milky Way, because it looks like a band of milk or white light. And that's all from all the stars that exist in our galaxy. The lack of light that you hopefully can notice comes from all the dust that's in the plane of the galaxy. So the key to studying the center of the galaxy is to go to infrared wavelengths. So infrared is long word of what your eye can detect. It's where your TV remote control works. And it's long enough that it can penetrate through all the galaxy. Okay, so the key is infrared. And this is what UCLA understood so well to capture, was the ability to work in the infrared, to develop instrumentation and methodology that operates in the infrared. So we're really one of the best places in the world for infrared astronomy and astrophysics. And that's essential technology for getting to the center of the galaxy. One of the essential technologies, and I'll get to the other in a second. Okay, so if you want to prove that there's a black hole, what you want to be able to do is discover the stars that are as close to the heart of the galaxy as possible. Because we're going to look to prove that there's a lot of mass inside a small volume by measuring the motions of these stars. And these stars move under the gravitational influence of whatever's in the middle of their orbit, for the same reason that the planets orbit the sun. It's just gravity. And remember, we want to show that the mass is in a small volume, so the closer you get to the center, the better off you are. In the early days, I should have mentioned, the first proposal we submitted was for 3 years. So it's actually rather amazing that roughly 10 times more later, we're still at this. And it's because the technology worked way better than we could possibly have imagined. And it's developed even further. So the scientific richness of what's possible has really grown beyond our wildest imagination. So in the beginning, we were just thinking about measuring how fast things move, not full orbits, just how fast they're moving. Closer to a black hole, the faster things should move. But if you have the time and the patience, and if people start saying, we don't believe your results, you're going to keep going and do the more robust thing of measuring the individual orbits. So I can tell you why those two things are different, but it really represents a different stage of the work that basically took a much longer time. So that was stage 2, and we're on to stage 3. Okay, so Keck is the largest telescope in the world. It was a radical new telescope design. I mean, people really didn't believe it would work. And telescopes are characterized by the diameter of the primary mirror. So this mirror is 10 meters in diameter. And to give you a sense of scale, that's like the width of a tennis court. And rather than polishing one single mirror, it was built of segments. Okay, so that was the radical departure from historical design, and it's actually the architecture that's been adopted by all future subsequent telescopes. So James Webb, which has just been launched, is also the same segmented design that was pioneered at Keck. There's two of them, and hopefully you can get a sense of scale. Those are huge SUVs down there on the bottom. I mean, those are the biggest ones you can buy. So those are not small, those are not mini ones, those are big ones. This is up on the summit of Moderator, which is an interesting place to work. So Hawaii, turns out, is one of the best places in the world to do astronomy. It's just got everything that you need. It's high, so you get through most of the atmosphere, and the airflow is really smooth. There's no city lights, so it has all the attributes. So there are a dozen telescopes from all around the world up there, in addition to the Keck telescope. Now, these big telescopes, the promise is both to see things that are faint, because you have a big diameter, big aperture, so like a big rain bucket with a big opening, so you collect a lot of rain. But the second reason that big telescopes really help is that the bigger your telescope, the smaller the detail that you should be able to see. So if you think about the technique of pointillism, seeing painting with little dots, and the closer you stand to those paintings, the better your ability to see the individual dots. The bigger your telescope, the better your ability to see the details of the universe. Okay, so that's the benefit of having a really big telescope. One of the challenges of that, especially for the telescopes that are on the Earth, is the Earth's atmosphere. The Earth's atmosphere is great for us. It allows us to survive here on this planet, but it is a total headache for people trying to see through it. It distorts your images of astronomical objects. And the analogy I like to make here is it's like trying to see a pebble on the bottom of a moving stream, that your vision of that pebble is completely distorted. So I've spent most of my career working on developing techniques for taking the blurring effects out of the Earth's atmosphere so you can get to that theoretical limit. Lots of solutions to this, including launching space telescopes. So this is a picture of Hubble Space Telescope. And of course, we've just had the incredibly successful launch of James Webb Space Telescope. But those are actually smaller telescopes than Keck. This one, Hubble, is 2.4 meters, James Webb is 6, and Keck is 10. And for the kind of work that I do, the benefit goes as the diameter to the 4th power. So that advantage, getting up to 10 meters, is a really important big jump. Okay, so I've done a lot. These techniques have allowed us to overcome the blurring effects. In the early days, there was a technique that was pretty hardware simple, but computationally complex, and only let you do the simplest thing. But of course, no one had done it, so it was pretty great. And I'm just going to show you a little bit of it. So we took these images that look like this. So they look like bug splat patterns. And we think of black holes in this box. And by playing these with image processing techniques, in other words, this is all algorithmic, it's nothing at the telescope, you can actually get rid of it and see the individual stars. So in other words, this idea that it wouldn't work and you wouldn't see stars is incorrect. And then this is a picture every year. Like, we didn't even need a computer to see them move. These things are hauling. And we have an image, it's much, much bigger, we see thousands of stars, but it's these stars that contain the answer. So you can probably identify my favorite star in the universe. It has the unimaginative name of SO2. Probably that's a better name. Okay, so those were the early years. Since then, the second half of this last 20 years, the last decade, has been greatly influenced by the development of hardware at the telescope. So now you want to introduce optics that will, in real time, correct for the blurring effects so that you can do much more powerful measurements. Okay, so the analogy I like to make, so you're going to see a couple of miracles happen, like the dome's going to go away. But we're going to be able to see the telescope. And you're going to see, so you can see the primary mirror on the bottom there, and the light will come in and bounce off some mirrors into where the instruments are mounted. And then we're going to look into this system, which is called adaptive optics. And what adaptive optics is trying to do is, if you think of the atmosphere as being a circus funhouse mirror that's distorting the image of you, the goal is to put another mirror in that has the exact opposite shape so that you look flat again, or the universe looks flat again. And that's called a deformable mirror. And the trick is that you have to operate that really fast because these changes are happening about 1,000 times a second. And you have to find some way of telling you how to move this. So the key is that little element up in the top right. At Keck, it's about this big. It has about 360 actuators that can move up and down really, really quickly. In a minute, we're going to see a different depiction of light. So rather than a beam of light, we're going to see what's called wavefronts. If there was no atmosphere, the wavefronts would be flat pancakes. But instead, we see Pringles potato chips. And, that's the mess. That's what creates that mess that we were looking at, the bug spot pattern. Now we're going to close a feedback loop that allows us to figure out, and that's a lot of computational work, real time, how to move this deformable mirror so you get the flat pancakes again, and you get a much cleaner image than we could ever do before. So this is a great advance, and in large part it came from developments in the military who also care about imaging both up and down. So it's a great story of technological transfer. And of course now the astronomers just have to figure out how to use this for astronomical physics. A key part of this is creating something that you can look at to tell you how to move that deformable mirror. We use lasers. It makes for beautiful images like this. And it takes advantage of a very wonderful fluke of nature. So if you go out and look at meteor showers, that's meteors coming through the atmosphere that are losing sodium atoms. It turns out they get trapped up at 90 kilometers in a very small layer. So we have above us this layer of sodium. So we take a sodium laser and shine it up to that laser and stimulate those sodium atoms to shine. So we make an artificial star, and that's what we look at to make those corrections. So lots of different technologies that are required to make this game work. Okay, so we and it works incredibly well. It allows us to make measurements that we couldn't have dreamt of in the first 10 years. Today, the animation that I was showing you before, but now no longer looking at real data. This is a model of the data showing you how these stars have moved. You can see my favorite star, SO2. It's the most powerful one because it's gone all the way around and some. With both images, which is what I've shown you so far, but with adaptive optics for the first time you can take spectra, which allows us to measure the motion along our line of sight, which is in the same dimension. Anyway, so SO2 is the most powerful one, but you need all the other stars to figure out what's going on. So what does this tell us? It tells us that when we went into this experiment, we knew that there was 4 million times the mass of the sun inside a giant region, lots of stars, gas, and dust. There was no opportunity to claim that this was a black hole. And what this work has done has shown that 4 million times the mass of the sun is actually dominated by mass that's contained in a volume that's a factor of 10 million times smaller. That's a huge advance. So that's how much we've moved the case for a black hole, is by a factor of 10 million, moving the case for a black hole from a possibility to a certainty. Another nice scale to think about is that this 4 million times the mass of the sun, so 4 million suns worth of mass is inside a region that corresponds to the size of our solar system. And this is the best case for the existence of a supermassive black hole, not only at the center of our galaxy, but in fact anywhere in our universe. Okay, So this is no long, so ta-da. I wanted to share this picture because this work has been done in competition with this other group. And I think it's really important to acknowledge the benefit of competition. It's a way of celebrating also the diversity of thought, that different perspectives really lead you to a greater understanding. I mean, while it's not simple to compete as a young scientist for 20 years with a group. I mean, he was a director of the Max Planck Institute when I first joined my faculty job, or got my faculty job here. So it's been an interesting process of competition, but I think we've all gained tremendously from the existence of these two groups. So I'm really delighted that the Nobel Committee decided to recognize the contributions of both groups. Okay. Let me just briefly, I don't want to go into too much depth because I think I'm basically out of time, right? Okay, I'll leave you with a teaser. One of the things that is so wonderful about what I like to call technology-enabled discovery is if your technology radically changes your understanding, your ability to measure, you tend not to not only answer the questions that you set out to answer, but you discover new questions that you didn't even think to ask. And that has absolutely been the case with this study. Almost every prediction for what we should find around a supermassive black hole has been inconsistent with the observations. This is like being a kid in a candy shop. I mean, we've got so much more to study. And this animation, which I love, it is a collaboration with the University of Illinois Advanced Visualization Lab, encodes a huge amount of information in terms of what we're learning. And just to give you a little bit of information, one prediction is that you shouldn't see any young stars. Young stars are very fragile entities and need to be able to take these giant tenuous clouds of gas and dust and collapse without being torn apart. Well, black holes tend to like to tear things apart. That's the nature of what they are, the nature of the beast. So the prediction is no young stars should be in this environment. All the blue-green stars, those are all young stars. And what do I mean by young? And again, I'm going to use some bad analogies. So if you say that typical life is scaled to a human lifetime, these young stars are like a human gestation period. So they're really young. So the analogy of baby stars really work. And they're the most common kind of things we see. And you might have noticed that there's also, as we pull back and sort of see the orbits that we measured from different angles, there's a clue, there's a really important clue, because many of them share a common orbital plane. So there's actually lots to be learned from people studying how planets form, because this just looks like a scaled up planetary system. So there's been lots of opportunities to collaborate with people in really, really different fields. So I like to call that the paradox of youth. How do we get these young stars? And I think we have some ideas, but it's not solved. One that we have even less ideas about are the old stars. So these are a billion years old. Those are the orange stars. The prediction is there should be tons of them. Think about a party. The black hole is the life of the party. Everybody wants to congregate around the life of the party. So the prediction is that there should be a huge concentration of old stars around the black hole. And yet, what we see is a dearth of old stars. So where did they go wrong? Where did they go? And it's an important realization because we actually use the assumption of this congregation of old stars to infer the presence of supermassive black holes elsewhere in the universe where we can't do these kind of orbit measurements. So that's a surprise, and a surprise that has implication far greater than just in our own galaxy. And the pink stars are the things that we didn't even think to make predictions for. These are objects that we see as they come by the black hole. They develop these tails. So if you've seen Interstellar and you've seen the giant tidal waves on the planet, those are from tides from the black hole. And it's like those waves lifting off the planet. So that's what's happening to these objects. And again, didn't even think to make predictions about these guys. And you need objects that are about 100 times larger than anything that was predicted to exist in this region. And we've come up with some really cool ideas that actually might be explaining mysteries seen by the gravitational wave community. So to me, this is super fun. And I've come to appreciate from a journalist recently that it's not so obvious that scientists like to be confused. But in fact, it's the moment when you know there's discovery just beyond your fingertips. So it's been a delightful project to be part of. There's way more that I haven't shared with you, but it has been an absolute pleasure to work at UCLA. It's the kind of institution that has your back and that allows you to succeed. Thank you for your attention. I'm happy to take questions. Yes?
I thought in perspective, there's stories on the top of Chile, the mountains of Chile, and
I didn't. So in fact, my competitor, those are the telescopes they use, are the ones in Chile. They're in the Andes. And in fact, it's a nice way to share the kinds of locations that astronomers like to use. So you want to be on a high peak. You want to be through as much of the atmosphere as possible. So the Andes and the summit of Mauna Kea both achieve that. And then you want to be around or near a big body of water, because that makes the airflow very smooth, or what's called laminar. So you tend to find these big facilities, these big telescope facilities on high peaks near big bodies of water. So the Canary Islands is another location that's ideal for this kind of work. Yes?
So I have two questions back there. Is our galaxy being drawn towards the black hole?
So no, actually, no, the black hole, you could take the black hole out and our galaxy wouldn't care too much, turns out. I mean, we think it's important in terms of the formation. It's an outcome of the formation. And in fact, one of the ways in which you can kick black hole, today we think most galaxies, probably all galaxies, form with these supermassive black holes at the center, so one per galaxy. And we also know that galaxies over time will merge. So we're actually on a collision course with Andromeda. But you don't need to worry, because what's going to happen, it turns out the distances between stars are really great. So the stars aren't going to collide, but they're going to merge into one giant galaxy. And then the most massive things in the system will sink to the middle. It's almost the same reason why you expect a concentration of old star. They're going to sink to the middle, and they're going to merge. And sometimes in that process, you can kick one of them out. So that's how you can get rogue black holes wandering through the universe. Yes?
I saw on your website at one point that through your research you might be able to calibrate the Hubble constant. I was wondering if you could talk about that.
Yeah, I mean, it's one of the ways in which we're super excited about really precise measurements of SO2. So SO2's orbit allows you to do two really important things. One is to just get the distance to the center of the galaxy. And in astronomy, there's this thing that we like to call the cosmic distance ladder, which allows us to build up our understanding of scales in the universe. And there's all sorts of bizarre outcomes of this calibration, including the conclusion that the universe is accelerating from itself, which invokes this concept of dark energy, which is really weird. And so you always have to ask, well, did I do my calibrations correctly? So getting a very precise measurement to the distance of the center of the galaxy is calibrating one of the earliest rungs of this ladder. So I think this is probably the first time I've ever been asked about this in a public lecture. So that's one of the deep, geeky things we're really excited about. So thank you for that question. And then the other thing that I'm really excited about is the idea that we can, or the opportunity, that we can test how gravity works with these precise measurements. And what's so exciting is that to get a seat at the table to do both the precision distance measurement and these new tests of how gravity works, you need a complete orbit. And this goes around over 16 years. In other words, to get a seat at the table, you gotta work for 16 years. Well, we're there. And so you know the geometry. You basically know where in space this object is. So you can start to look for Einstein's predictions. And what is he really predicting? And the simple way I like to think about this, I mean, it's not that simple, but it's the idea of that near black holes, space and time mix. This is that classic gravity well thing. It's basically getting rid of one dimension in space and using it for time. So as you get close to the black hole, you get more mixing of space and time. And all sorts of weird things happen. Like if we were to watch somebody that you wanted to throw into the black hole, and I'll let you choose. It's not going to be a good trip for them because they're going to be torn apart. But we're going to see them get slower and slower and slower and just stall at the event horizon. And that's because of this mixing of space and time. So what's so exciting about these measurements is these are the first tests that are really close to this event horizon that test that mixing. And there were two tests, and don't worry about the words, one happened in 2018, and one is emerging as we go towards furthest approach in 2026. The first one behaved well. The second one is doing the exact opposite of what we expected. So the expectation is that, like a kid's spiral graph pattern, it should go in the direction of the orbit. That's what gravity says should happen. We're seeing it go at twice the rate in the opposite direction. So again, wonderful fun. So either you're doing something wrong, like you haven't calibrated your measurements right, so you have to think deeply about what you're doing, or you've made a discovery. So if you take this seriously, the fun part is that the way you could explain this physically is the presence of dark matter at the center of the galaxy, which would be just so cool, but I'm not sure yet. Yes, in the back.
What will be the 3-sigma confidence interval of the mass of the black hole at the center of Milky Way?
So how could we increase our confidence about what the mass is?
Yeah,
So this will do it. So I mean, all of the measurements, if you keep going with the measurements not only of SO2, but what I like to call SO2 in friends, basically everything that's close enough that it's that have orbital periods that are comparable to a human lifetime. Actually, I should be talking to Todd about the digital archives. Like, I should be keeping these measurements for my students so they don't go away because these periods are really long. Yeah, the mass, more precise mass will come out of that. And that's interesting, but no, I think it's no longer the thing that's the most exciting frontier. So I think this idea of testing how gravity works near a black hole whose mass we know pretty well is really one of the most exciting frontiers. Yes?
I'm interested in your trajectory. How did you go from a high school to college, and who helped you to keep these passions going so that you came to where you are today?
So if we start in high school, at that point I understood I had a real aptitude for math and science compared to writing or history. Of course, there's irony there because, of course, today I have to write a lot and speak a lot. So it was pretty clear that I was super interested. Again, hindsight's 20/20 in terms of how you understand what interested you. But when I was young, the moon landings happened, and I started thinking about space and time. And I'd say it both fascinated and terrified me. It really bothered me to think about the scale of the universe and boundaries. And I really saw that as a math problem, so I went off to college wanting to be a math major. But that probably tells you more about my dad, who thought math was the queen of the sciences. So he was trained in Geneva and just thought math was everything. He was an economist. So, you know, my parents were a huge piece of this. Teachers were a huge piece of this. I think some of the most important decisions we make as students, especially the further we go, is who we work with. And so in grad school, you know, it becomes the be-all and end-all because they're the only people who evaluate you. So one of the things that's hardest to do in graduate school is actually change your advisor because we somehow feel that we're letting those people down. But it is something that I ended up doing in grad school, was realizing I had an advisor who really didn't have my back and changed to somebody who did. In retrospect, I've now come to understand, you know, there weren't a whole lot of women in the field, but what I didn't understand at the time, it totally makes sense now, is that my primary advisors as an undergrad and a graduate students both had daughters my age. So while they weren't women, they were very empathetic, I think, towards, you know, their own daughters. So I sort of think that's just interesting, but I didn't understand that at the time. I just understood who had, you know, you always know who has your back and who doesn't. And I think giving students the power to feel okay changing is one of the hardest things in grad school. At UCLA, I mean, you don't stop needing mentors just because you become a faculty member. And I have to say astronomy, the group there is not only very strategic, but very vested in supporting their young faculty. And that doesn't happen everywhere. So I really had some great mentors. Mike Jura, who has unfortunately passed, was a wonderful mentor. He's one whose advice I constantly think about. Actually, Todd and Jaime might appreciate this. I remember not getting a daycare spot for my second child. I was furious. And I walked into his office and he said, you know, this is what my wife tells me. Write the inquiry letter, tear it up, and help people do their jobs better. And that's a brilliant piece of advice about kind of redirecting or kind of owning your power in a productive way rather than I'm angry and I'm just going to shout way. So I really appreciate all the little gems along the road and appreciate that I'm part of a department that has that culture because I don't think that exists everywhere. Yes?
Can you say something about the information paradox and what's known about that right now?
The information paradox, not a whole lot. Black holes definitely introduce the information paradox because you can't get information from inside the event horizon. The only way that information comes out is in the form of Hawking radiation, which is a really small effect for these supermassive black holes, but is an important reason that nobody got too worried about little black holes being formed in particle accelerators. So I think that's the only constructive thing I can say. Yes, Len? Yeah.
A couple of weeks ago, a photograph of the Sagittarius A was published, and it's the only second black hole that we have pictures of. Could you tell us what is the importance of being able to actually get a photograph from a scientific point of a black hole?
Okay. So there's a lot of ways to ask this. I'm going to ask you guys a question. Can you take an image of a black hole?
No.
No. Like, black hole by definition doesn't emit light. So I think this has been a very exciting result, but to understand what you're actually looking at is a much more complex question. So I think this experiment has been really fascinating, both from science and just sociology, actually. The sociology of science, the sociology of media. So it's really exciting. What they've done is a technical, huge achievement, but not in the way you might think from reading the newspaper. So people have been able to take telescopes from all around the world at radio wavelengths. We were talking about radio wavelengths earlier. And to get really high resolution, radio wavelengths are easier to deal with because they're really long. So you don't have to care so much about the optics. On radio telescopes, you can walk on them. If you breathe on an optical telescope, somebody's going to get mad at you. So they're just easier to work with. So it means you can combine the light from telescopes around the world. And we've been able to do that for 50 years. So you might think, oh, so there's been a lot of buzz about that part of this experiment. And the buzz is because they, for the first time, worked at much shorter wavelengths. And the technical achievement with that is you have to be able to tell time really precisely. Again, not an easy thing to talk about, so it's much easier to say we've made an image, the first image of an Earth-sized telescope. But that's the actual achievement, because we've been doing the radio interferometry for a long time. Okay, so I'm going to be maybe, this I would never tell a reporter, or say to a reporter, because it's not positive enough. So you can also ask, well, what does it mean to take an image? So an interferometer has different pairs of telescope, which is like getting a part of the image. So you have incomplete information, and it's a really interesting problem, and even a greater problem for the center of the second one, the center of our galaxy, than the other galaxy. And I can explain more why people are interested. But let's just leave it at, that's an image that has a lot of information as a starting point. So what are you taking an image of? So let's just agree that there's something about what you expect to see already encoded in that. But what people are expecting to see, and that is truly exciting, is you're seeing a ring that comes from what's called a gravitational lens. So black holes, through this bending of space and time, right, this thing, means that light won't travel along straight lines. And one of the consequences is that something that's sitting right behind it, like if you have an emitter, a light bulb at radio wavelengths, what it will make is a ring, and a ring at roughly of the place that they're actually seeing it. So that's another confirmation for how gravity works. Now they actually need our measurements of mass and distance, so that's the way in which we collaborate with them. So it's super exciting, but I just have a minor pet peeve with the image of a black hole. So I've shared that with you. Okay, thank you for your attention to this.
Dr. Ghez, we are awed by your brilliance and inspired by your enthusiasm. I'm so excited that you seek encouragement and curiosity from those who say no, from the challenges. I'd like to very quickly, with your indulgence, read to you this award. The 2021-2022 Leve Award is presented to Andrea Ghez. The Leve Award is a biannual award that recognizes and celebrates the contribution made by a person whose ideas, values, or accomplishments have had a positive impact on the world, the Jewish community, and our humanity. Congratulations, and we thank you so much.